Hello, welcome back to my bench. Today, I've got a problem. I've got to fix this radio that I'm working on. It has to be done like tonight. And I've got some capacitors I need to replace. But I'm not in my normal place and I don't have any of my equipment. I don't have any capacitor testers or anything like that. So I found some caps that I know are bad in the radio, and I want to replace them, but I don't know if any of them are any good. I do have a oscilloscope, which is right here, and I have a function generator that'll create a square wave. So we're going to see if I can find out if these caps are any good and how they hold up under certain conditions. And yes, it can be done. It's just a little bit finicky. So, what I've got here is a capacitor or resistor substitution box. I'm not crazy about this one because when they're all off, it's basically a short. I wish it was open, but it doesn't work that way. What you do is you just put in what you want for resistance. In this case 1K, and you can add them up as you go. It goes up to 4, 5, 6, 7, 8, 9, 10 megs plus the rest of them. It's fairly accurate. It's okay. It's an Elenco. This kind's been around forever. So I got this, and I got my capacitors and my function generator. My function generator is set on 1 volt output at 1000 hertz, and feeding into a 50 ohm load because that's what the function generator takes as an output. And the scope is my LaCroix 9314L. You don't need anything quite this fancy. It's just this one's a whole lot easier to read, so we're going to use that. So what are we going to do? Well, in order to get the reading off of a capacitor, you need to give it two things. You need to give it a square wave output, and you need to give it a resistor in series with it so that you can measure how much time it takes for that capacitor to charge. And from that, you can determine the capacitance and a couple of other things which we'll play with as we go along here. So what we're going to do is we're going to take, this is my scope leads. These are just going straight into the channel 1 of the LaCroix. And we'll put capacitor right across the leads. This is the ground coming from the function generator. We'll put it on the same side of the cap as the ground for the scope. This is the function generator coming into the substitution box. This is coming out of the substitution box on the blue wire, and we're going to hook that up to exactly the same side as the scope. As you can see, we have a square wave. Very nice square wave. It's pretty. We also have no input, no resistance whatsoever. The idea that we want to do here is on the scope, we want the square wave to not be quite so square. We want it to have a certain amount of slant so that you can measure it. If we pull this out now, you can see that it's pretty square. I mean, it's, what is it, timing-wise? What are we on? We're on 2 microseconds. So it's less than 1 microsecond rise time on there. Well, that's not going to help us because that's just measuring right across that capacitor. However, let us give it a little bit of resistance here. bring this down so you can see it. I'm going to give it, 10 ohms. We'll start with 10 ohms. Oh, absolutely nothing happened if you watch the scope. Okay, let's go to 100 ohms. Still, nothing happened. Let's go to 1,000 ohms. All right. Now, you see what we've got here? We've got a small difference between when the capacitor gets the voltage and when it charges up to its full voltage on the top. Over here, we'll look. I'll pull this up right down to the bottom for that bottom pointer down there. I don't know how well you can see that, but it's right there. And then we'll pull the top one up to the very top. And if you look over here, we got 0.995, 1 volt. All right? Well, in order to measure a capacitor, its rise time, how long it takes to charge, you have to measure from here to 63% up here. So you come from the bottom, where it starts to charge, to the 63.2% where it's charging. Okay? Not 100%, 63.2. Why? I got to do something here real quick. I want to redefine A to average. That way it'll average it all out so it looks better. Okay? Anyway, so we want to bring this top one down. Since it's 1 volt that we're putting in, we want 630 some millivolts. Well, this drops like a rock right here. And this scope has a neat little function. You can push this button and zoom in and move it across so that you can zoom into this section that's a brighter yellow. Okay? So if you look down the bottom down here, this is our bottom. It has the pointer with the little cross on top of it. If you can see that, that means it's sitting at 0. And then we'll take this other one, and if you watch over here, we'll bring it down to 632 millivolts, or 63.2%. And we come 800, 790, 780. Come on. A lot of turning here. 632. Oh, 632. Okay? So we got 632, or 0.632 of the way up the curve. All right? Now, if you look down the bottom, you'll see it says 24.3 microseconds. So it takes 24.3 microseconds to go from where it starts to charge up to 63.2%. Well, if we take that 24.3%, let's pull up a, hang on, I gotta get something. Okay, I had to go get the calculator. So if we take that, what we've got, 24.3 microseconds, so that would be 0.123, those are the millis. The next is micros. 1, 2, 3, 2, 4, 3. So we've got millis. 24.3, so that's 24.3 microseconds. And we want to divide that by the resistance that we're using down here, which is 1,000 ohms. Well, this box introduces 5 ohms, so we're going to do it with 1,005 ohms. So we got divide by 1,005. 0.05 equals. Well, we end up with 2.4179, whatever it is. And if we multiply that by 1 million, because we're dealing with micros here, we now have, whoops, that's not right. What did I do wrong? Okay, let's try this again. Clear. We got 0.0000243 divided by 1,005 ohms equals 2.4 to the negative eighth. So we want to multiply that by 1 million. And we end up with 0.024 microfarads. 0.024 microfarads. Well, what does this say? It says, can you read that? Come on. 223.022. So this is a 0.022. It works. This method worked. Well, that's great, but I want to find out something about this, so let's hook it back up. We gotta turn this to get everything back again. Now I want to find out, does that change much under certain circumstances? Well, this is a greenie cap. These are actually pretty good. I've got some duster here, which if you turn it upside down is freeze spray. So you watch right down here at that 24.3, I think, yeah, and see if freezing this will make any difference, because it might be in the cold. Did it change it? No, 24.3. It's still 632 millivolts. Freeze it some more. Nope, it's right where it should be. So it's not affected very much by cold. Let's turn the hot air gun on, and we'll take it down to, I don't know. Let's make it hot in that room. Let's make it 100 degrees Celsius. I wouldn't want to be there. That's as far down as my my heat gun will go. It's dropping, or trying to. It takes it a while to drop. All right, we're going to give it some heat now. Let's see if anything changes. All right, ready? Here's our heat. Anybody changing? It's wiggling a little bit up there on its values on the top. Getting a little bit of noise. That's 175 Celsius. So, nothing really changed. Well, that's cool. How about structurally? Let's bang on it with something. Universal banging tool. No, that doesn't appear to make much difference either. All right, well, let's test another one then. That's kind of warm. Okay. How far down can we go? Let's see. Here's a .047. One of these little guys. We'll hook him up. Now, when we do this, we're going to have to change this too. The idea is you want to get that as little a knee as you can, but you've got to be able to see it and measure it. So, what do we got now? Well, we got... Let's try it. That's still 1K. How about 400 ohms? Nah, that's not enough. Yeah, I think I'll go for that. That's 700 ohms, 4 and 300. So let us... One of the things that's annoying is you have to take it off and turn it back on again here to get this math to catch up. All right, so we want 632 millivolts. That's what we've got. And we've got 0.31315. So let's clear this. So we got what's that? 31.5 microseconds. 1, 2, 3, 0, 3, 1, 5 divided by 705. 705 equals 446. Okay, so times 1 million. 0.044, and this is a 0.047. So that's working out too. So let's hit it with a freeze spray and see what it does. You watching? Ooh, no, that's not good. That shrunk it down quite a bit. We are now... Oh, that has a big effect on it, doesn't it? We want 632 when it's cold, and it's 0.393. So if we go over here, clear this out, and we go 0.393 divided by 705, we're now up to 5.5. 5.5 microfarads, or yeah, 0.055 microfarads. Boy, my tongue's getting tied up, and I can't see what I'm saying. Anyway, so that really makes a big difference. Let's heat it up and see what this does. We're heating her up. Heating. Oh my goodness. All right, well, now, what does this give us? In a 100-degree room, evidently, or a 100-degree box, yeah, come on. Getting kind of hard to get there. It's wiggling about a bit. Okay, that's close. We are now at what? 0.359. Heated up pretty hard, so that's going to give us 0.000359 divided by 705 equals 0.047. So it took it back up a little higher than it was by heating it up. And if we hit it up a lot without melting my leads here, look at that. We're way off. I got to do this pretty quick. All right, so what are we? 19.3. So, clear this out. 0.00000193 divided by 705. No. 0.000193 divided by 705 equals, it took it all the way down to 20.027 microfarads. So these things, these little guys are they're affected by heat and cold. We don't know about their ability to withstand getting the junk beat out of them. Lost a lead here. Let's see if we can get this down and kind of tap it a bit. No, that doesn't seem to affect it very much. All right, so we know how those two work. Well, let's get into something. We'll do something a little bigger. This is about as big as you can go. This is a 0.22. We'll hook it up. Just like we did the other one. And see that form? You do not want that because that doesn't even reach the top voltage. So we got to get rid of our 400. Give it a 10. No, 20. Maybe 30. 30. That looks good. See how it's still fairly square? So let us bring up the math again. Go down to the very bottom where a little line comes on top. Come on. There it is. And we want 0.6. And that's reading what, 45 microseconds? I don't think that's going to be right, but let's find out. So 0.000045 and we are sitting at 35 ohms divided by 35 equals, yeah, you can tell right away that's not right. So we're probably going to have to go down to 20 because that just brought it in too far. You got to be careful when you're doing these. And the bigger they get, the harder they are to do. All right, so let's see. Yeah, I'm only sitting at 700, 800. But the voltage doesn't matter. It's the 0.6. Well, it does matter because your maximum excursion here is what? No, it's 1. It's up here. It's 1. All right. So let's bring this back down to 0.6. 3. 2. What do we got? We got 45.1. Okay. Clear. 0.000451, and we are at 20 ohms. Divided by, it's going to be 25. So we got nope. No. like I said, reading these is very difficult. We got enough there. We're going to try it on 10 ohms. The big ones, if you give them too much voltage, they collapse. Well, if you give them too much resistance, they collapse. There, and point. Six, 3, 2. We're looking at 9.725. That might be a little closer. Let's clear this out. 0.123, 1, 2, 9, 7, no. 9275 divided by 15. Now, you can have a really hard time measuring these big ones. These like this. This is a 0.22. This method just, you can't get accurate enough to do it. However, here's a 0.1, a really good 0.1. Let's hook it up. All right, and try 100. Maybe. Yeah, that looks fair. Let's zoom out a little bit more. Take the top one down to its bottom, where the little line comes on. Take the top one up to 6, 3, 2, 1, 7, 1, 6. I guess that's close enough. We got 14.5 microseconds. 14.5. All right, so we got 0.123, 145, and divide that by, we're sitting on 100 ohms here, so 105 about, and times 1 million. So we're looking at 0.142. Like I said, that's about as big as you can go and be semi-accurate, is that 0.1. However, and these things are not reactive to anything, heat, cold, these are great. Let us see how far down we can go. Here is a 22 picofarad. Little junky. One of those, not even an NPO. Well, it's got a black dot on the top. Maybe it's an NPO. I don't know. We'll find out. We'll heat it up and see if it changes. All right. So that's 22 picofarads. Now, we're going to have to go some on resistance. Let's start off with 1K. Nah, that doesn't make hardly any difference at all. Okay, let's 2K. You barely see it move. 3K. No. Wow. $4K? Okay, just barely gets a knee there. Just barely. So let's bring our markers over to here. And up to our 6.32. Right about there. And what are we looking at? 795 nanoseconds. Wow, that's getting down there. So if we do point millis, micros, 795, and we're going to divide that. We don't really care so much now. We got what, 4K? 5 ohms isn't going to make any difference. 4000 equals, wow, look at all of them. So we got We got millis, micros, nanos, and picos. So this is saying it's 19.875 picofarads. Cool. And it's a 22. Well, let's start off. Let's heat it up and see what happens. This should be fun. Okay, heating up of the 22 picofarad up to 100. Boy, it's not doing much, is it? No, let's bring this out so we can see it. Where's my delay? Stand it off. We're starting to pick up noise here. Boy, it doesn't have much effect on it, and it's blistering hot. Let's try some of this. Yeah, that affected it some. That took it down, but not by a heck of a lot. What is it? It's bouncing around pretty bad. Yeah, 626, 631.5. Let's hit it again. 631.5, and way down at the bottom, right there, we got what, 717. So we go 0.000000717 divided by 4,000 equals 0.195. It makes very little difference. So I guess the little black cap on there, see it? See the little black cap? I guess these things are NPOs. I didn't know that. Anyway, there you go. There's a little lesson on capacitors and how you can measure them without a capacitor tester. And it ain't all that accurate, but it'll work. It'll do okay for you if you just need to get something close to what you wanted, and you've got a scope, a function generator, and a resistance box. You can just use a bunch of resistors. You don't need the resistance box. It's just a lot easier to flip them in and out. Anyway, well, I hope you enjoyed it. There's our first capacitor lesson. The next one we're going to do is capacitors and what they actually do in circuit. So don't forget to well, if you're here, you're here. You're a patron. So thank you very much, and I appreciate it. And I hope you enjoyed it. Give it a thumbs up or a like on here, and I sure appreciate that. Till next time.